Welcome back, everyone, after that short break, and welcome everyone who's joining on the virtual platform as well. After a very power-packed first session on renewable energy storage, we are going to be talking about the next session, which is more on improving access to affordable energy and local energy communities. We have a panel that I'm going to shortly invite and introduce on stage over here, but moderated by Ram Narayanamurthy. I'll introduce Ram in a minute. May I invite the in-person panelists on stage, please? Mr. Krishna Jayaraman, Karthik Jayaraman, Satya, and Krishna Vasudevan. We do have Professor A. Mani also joining in on the panel. He will be joining virtually. And we have Mr. Ravin Mirchandani, who is also joining us virtually. So let me introduce our moderator for today, Ram. Ram has over 23 years of experience in technology and innovation. Ram has served as the Chief Science Officer at Ecoforce Incorporated and is currently a technical executive focusing on decarbonization of buildings and communities at the Electric Power Research Institute, EPRI. Ram is also our alumnus, a 1996 mechanical engineering passer. I invite Ram to introduce his panel and to talk on improving access to affordable energy and local energy communities.
Thank you, Nikhil. And I hope everyone can hear me okay. So thank you very much. It's been fascinating just listening to the conversation over the last day and a half. And I also wanted to say thanks to the faculty team at IITM for putting this together. And it's been an honor working with the IITM alumni team as part of putting the conference together. So thanks to everyone who supported this. So the prior panel talked about how we are going to decarbonize what we call the front end of the energy system, how we get cleaner energy, how we transmit that cleaner energy, how do we get it to our customers, right? Ultimately, the goal of the energy system is to provide a service to the people who use it, provide that service in a reliable manner, provide that service in an affordable manner. And that's what we're going to talk about, how the different panelists today are achieving that goal of providing affordable, reliable energy and working in local energy communities to increase access to energy for the population as a whole. So it's a very fascinating panel. We are going to touch multiple aspects of it. We have a couple of people on the panel who are actually customers looking for that affordable, reliable energy. We have others who are actually providing that affordable, reliable energy. And then we have our great faculty at IITM who are working on creating the technology platform to be able to do that. So with that, let me just quickly introduce our panelists. And then the format of the panel is going to be, we are going to have presentations from the IITM professors. We will do a little bit of an overview of the energy system. I'll provide a little overview of some of the work we have ongoing, look at that perspective from outside India. And then we will have our industry panelists talk about their company and their work, and most importantly, what their needs are for being able to provide this affordable, reliable energy. And then after that, we will have a panel discussion to match the needs of the panelists, the industry panelists, with the research that's going on, the work that's going on at IITM. And hopefully we'll have some time for Q&A from the audience. So with that, thank you, everyone, and welcome everyone to the second session of the day. So with that, let me, Dr. Krishna Vasudevan is leading the Center of Excellence on looking at local energy communities and microgrids at IITM. Dr. Mani is working on better desalination, more desalination using renewable energy, looking at more reliable and more cleaner ways of providing cooling, both for cold storage and for providing comfort cooling. Mr. Ravin is the lead, is the CEO of Adore Power, and they're working on doing microgrids, which given the nature of India and how we have our transmission distribution grid spread out and the challenges, microgrids are a really critical part of how we can provide affordable energy to everyone. And our last panelist is Mr. Karthik Jayaraman, and Karthik is CEO of Way Cool Foods, and he's going to provide the perspective of how, as a customer of this energy system, what he needs from it, and some of the technologies that they are looking at in as a way to enhance the supply chain and improve food security, but bringing energy into the mix in the food production area. So with that, I just wanted to go around the horn, have the panelists provide a deeper introduction of what they do, and then we will jump into the presentation. So with that, Dr. Krishna, can you provide a brief overview of your work and then introduction to your work?
Ram, may I request Mr. Ravin Mirchandani to go first, because unfortunately he has had a complete power failure and he is working out with candles. So while we have him, let's hear from him first.
Okay, so thank you, Nikhil. Ravin, please go ahead. It's interesting. I think this emphasizes the work you're doing and you're trying to do. So please go ahead, talk about your company, provide us an overview, and then hopefully you can stay on for the discussion at the end too. So thank you.
Thank you very much. Can I just get you to confirm you can hear me okay?
Yes.
We can hear you well.
Excellent. Thank you so much. I thought I was going to miss this. I had a fire in my electric room 2 minutes before the start of the panel, and we had the fire extinguishers going. And so we've got no power right now, but I got candles and I've got my Geo dongle. So hopefully that survives. So it talks about microgrids and disconnected communities quite well. So thank you for having me on the panel. My name is Ravin Mirchandani, and I am the chairman of Ador Powertron. Ador is a 115-year-old Indian group, and we have conventionally made transformer rectifiers for electrostatic precipitators for coal-fired power plants. But our focus over time has become hydrogen, and to make DC power sources for hydrogen electrolyzer plants. So we make these in Pune and supply them around the world to over 75 countries. And now we're also working on hydrogen power projects in India for disconnected communities. And I hope my power stays long enough for me to be able to present it. It is to use solar and wind to create or generate hydrogen, which can then be fired through a fuel cell to give you electricity at times when wind and solar are not available, which is quite interesting for parts of India, for example, the Northeast, the islands such as the Lakshadweep or the Andamans, and also parts of fringe of grid in Uttar Pradesh or Bihar, where it is too expensive to wheel power, and power is taken by diesel, or power is provided by electricity at subsidized rates because it's politically convenient to do so, but at an immense expense to the taxpayer. So how do you use solar and wind in these sorts of locations to generate electricity and hydrogen to give you 24/7 power is what I want to talk to you about today. So thank you very much for having me on the panel.
Thank you. Would you like to just go ahead and do you have a presentation, or you just want to?
Yeah, are you all right if I do that? Because I've got enough power if you want to introduce the rest of the panel, and then I can start, so that you just, I don't want to interrupt your flow.
That's okay. If you want to go ahead and make your presentation, I'd rather have you do the presentation then, and we can come back to the other panelists later. So, but hey, it's a great example of why we need the work you're doing. So please go ahead.
Excellent. So with your permission, I'm going to share my screen. I'll just get you to confirm that you can see my screen, and I will jump right into the presentation. You can. All right, great. Thanks, Ram. So I'm here to talk to you about how hydrogen will change our destiny. And I call it how hydrogen helps us basically delever ourselves from the tyranny of the hydrocarbon molecule, because forever we've been locked into the politics of the Middle East, because we have to import oil and hydrocarbons from the Middle East to give us energy, or import coal from Indonesia and Australia to give us energy. And hydrogen has the opportunity for us to be able to do this anywhere in the world. The modern economy is one, as you all know, where we have unclean air in any city, whether you're in New York or Sydney, or whether you're in Madras or Delhi. We are faced with pollution because of the way we live, and it's not dissimilar to how horse manure was polluting all of the cities around the world 110 years ago, when all we had was pushcarts. Hydrogen allows us the opportunity to delever from this, to give us zero emission energy, whether it's mobility or static energy. And if you see around the world, all of the countries around the world have released a hydrogen strategy, and India is no different, of course. We did as well. So some of the countries were first off the rank, such as Australia, Germany, Sweden, and others have been following, and India is no different. Hydrogen is the new oil, the new gold, the new plastic. Why is it so? Because hydrogen is an enabler. You know this, so I'm not teaching you anything new. Hydrogen allows you to firm renewable energy. The problem with renewable energy over all of these decades has been that when you have enough renewables, you don't have enough demand. And then when you have too much demand, you don't have the renewable energy generation. And hydrogen allows you to do this at a cost-effective rate and to store the energy rather than in a battery where you've got energy storage degrading over time in a molecule in a chemistry form that through a fuel cell brings it back to electricity. So you know this, I'm not teaching you anything new. Hydrogen for mobility from green energy basically is taking solar or wind through an electrolyzer into a storage unit, compressing it to 350 or 900 bar based on whether you're filling trucks or buses, and then filling at that location. It's a rather novel concept for India, but my argument to you is that in 5 or 6 years, it will not be uncommon for you to have a 1 acre block or a 1/4 acre block next to a fuel station or a hydrogen recharge station for you to make hydrogen from the sun immediately at that location, particularly in parts of India where you have abundant sun. A hydrogen fuel cell electric vehicle, again, I'm speaking to the IIT, so I'm not teaching you anything new, uses 90% less lithium than a battery electric vehicle and replaces that with a fuel cell that converts the hydrogen molecule back into electricity, charging the vehicle. So you know that the Toyota Mirai, you know the Tata bus, and the fact that there's numerous other companies that have committed to this. You have this schism in the world of automotive between battery electric and hydrogen. Companies like Volkswagen and Mercedes have committed to battery, and others like Toyota and BMW have committed to hydrogen. So you have two views on whether it'll be battery electric as a future or hydrogen. But the truth is, we'll have multiple sources of energy in the future. If you're doing short runs within the city, it'll be battery electric. And if you're a fleet, such as a bus or a truck or a taxi, and you need to do long distance, then it'll be hydrogen. So hydrogen for energy security is what I'm talking about. And that is using renewable energy, solar or wind, to run through an electrolyzer and then to store for an indefinite amount of time, run it back through a fuel cell, back to electricity when you need it. And this typically comes in a containerized solution, one container for the electrolyzer and the other container for the fuel cell source to give you energy. I'm going to run you through a few case studies where this has been made already possible across 2 countries, Sweden and Australia, and what we're trying to achieve as a result in India. So as a standalone power, why hydrogen is interesting? Because it firms the use of renewable energy. It replaces something like diesel, which is prone to pilferage, has an enormous amount of problems in trucking over long distances, and creates its own emissions during transportation. So as a standalone energy source, hydrogen basically comprises an electrolyzer, a compressor, some sort of storage, a battery, which is lithium or lead, typically lithium, a fuel cell, and then PLC controllers that manage the whole system. It's not incredibly complex. And in fact, it's going to be very easy for us in India to do because we have such an immense amount of experience in managing various forms of chemistry and electrochemistry and power electronics. If I was a betting man, I would bet that India is going to be a leader in this field, particularly because all of these in the ecosystem, except lithium-ion cells, already exist in India. What hasn't been done is integrating this together into one solution today. And what is that integration? As I've just said, it's a skid that converts renewable energy to hydrogen and another skid that converts the hydrogen back into electricity. It's not that complex to do. It's just a question of applying our minds and studying what has been done around the world. So what has been done around the world? I'm going to run you through 4 examples. The first one is a private home in Sweden, which is the most visited home in the world. It was also visited by Bill Clinton and our own former Prime Minister, Manmohan Singh. It's also been visited by Minister Gadkari. This home has been off-grid since 2016, running on solar and hydrogen. It has a 16 kilowatt solar plant that you can see on the roof. And it has a 4.95, so less than 5 kilowatt PEM electrolyzer in the basement, which you can see in the photographs there as well. And it has a very small amount of storage, 235 kgs of hydrogen at 300 bar, and a 5 kilowatt fuel cell. And this entire house in Sweden, with 200 days of rain a year, and the shortest days of sunlight in a year due to the far north location of the premises, is able to provide enough electricity for this house to be off-grid for the last 5-6 years now. What you see in the photographs here is the inverters and the battery storage, and on the right side, the electrolyzer that's running in the basement of this house. Here's some details on how much is produced over the years. So the solar PV power is 15,000 kilowatt hours converted into water electrolyzation at 3,000 normal cubic meters. There is enough hydrogen being generated here that in the winter, they do not need to shovel the snow. They put hot water pipes underneath the driveway, and hot water is heated using the hydrogen to keep the driveway warm. The second example I'm going to give you is a hydrogen recharge station. So this is a filling station for vehicles. So you can see a Hyundai and a Toyota hydrogen car here. This is in the town of Mariestad in Sweden. Again, another 220 days of rain a year, where there's not a lot of sun. Very small amount of solar, 250 kilowatts. It's a 1/4 acre block that sits right behind this filling station, 1/4 acre, 290 kilowatt alkaline electrolyzer. We have so many companies in India that make alkaline electrolyzers, and 450 kgs of storage. That's 2 big cylinders at 300 bar. Installed in 2018. Enough hydrogen being generated here for the city council to offer free hydrogen coming from the sun to anybody that has a hydrogen vehicle in the city. It's 100% off-grid, 100% green hydrogen generated from the sun for mobility. And the hydrogen production is 60 cubic meters an hour. 5.6 kgs an hour, or 60 normal cubic meters an hour. The hydrogen outlet pressure is 35 bar. It's boosted up to 1,200 bar because this is made for vehicles. Vehicles run at 900 bar. So it's stepped down from 1,200 to 900 bar to be filled in vehicles. Another example is this apartment dwelling of 172 apartments that have been off-grid. This is between Mariestad and Gothenburg in Sweden. Again, the reason I'm making the point of Sweden is they do not have a lot of sun. But they're running entirely on the sun, 600 kilowatt solar. So that's about an acre of solar, a 290 kilowatt alkaline electrolyzer with a very small amount of storage, 380 kgs at 300 bar. Peso in India allows us to go up to only 150 bar. I think it might have taken up to 200 bar. So you'd need an extra amount of storage in India because we can't store at such high pressure. And then there's 6 5 kilowatt fuel cells that are running to make this entire apartment complex go off-grid. In Australia, we're working on a project for a hydrogen recharge station that is also completely off-grid, and that is using the power of the sun to create enough hydrogen to fill hydrogen in tanks of trucks that are moving from Adelaide through to Darwin, and the distance from Adelaide through to Darwin is the equivalent of going from New Orleans to Chicago. So you can see the distance, and that's why hydrogen works, because it gives you an immense amount of distance on one fill. So this is a 432 kilowatt electrolyzer and 125 kilowatt fuel cell. So you can see these are actually quite small ratings. Everything that's being tendered in India today is 5 megawatt plus. We're going for the large end of the scale. And I'm here as an argument to say, do not ignore the small end of the scale, because we have an incredible amount of communities in India that are inefficient to service, that eventually, as the cost of fuel cells and electrolyzers drop, we should be able to service in India. Finally, three slides. First, the announcement just this week of 15 hydrogen filling stations in Sweden that will be 100% solar green hydrogen filling stations, which leaves me with a lot of hope that you will see in the next 10 years something very similar in India. 1/4 acre blocks that use solar to generate hydrogen to fill trucks and buses on the highway, so that you do not need to be dependent on battery electric to do long distance zero emission travel. We're working on a project in the Maldives. The Maldives is interesting because electricity is very expensive, and they have one large project right now, which has been fought between China and India for a solar array. And you will see that in this project, the levelized cost of hydrogen comes to between 4 to 5 euros. So at 350 kgs a day from the solar plant, at a capex of 60 crores, and an OPEX of 28 crores over 25 years, so an OPEX of about 1.1 crore a year, you can get a cost of hydrogen of about between 4 to 5 euros a kg. The target for the European Union is to be at 2 euros a kg by the end of this decade. The cost of hydrogen in Europe today is about 6 euros a kg. And so what I'm trying to demonstrate here is you can already be lower than that in very complex environments where energy is very expensive to make using 100% renewables. There's two ways to look at this. And one is whether you have enough energy being generated by the sun, or whether you need to have some backup from the grid. And so in the previous example, I've shown you a larger capex because it's a larger megawatt system. But in the second example, we've used a smaller megawatt system, assuming some sort of backup from some sort of grid available to keep hydrogen being generated. That hydrogen then can be transported in cylinders to different islands. And in these islands, using a fuel cell being converted back to electricity, using the RE8760 system that you have seen being deployed in various projects in Sweden and in Australia. So I'm quite hopeful that what we're seeing here demonstrated in countries as far afield as Sweden and Australia with very different climates, one with a lot of sun, one with not, but still being able to survive off-grid for an indefinite period of time at a cost of energy that is slightly more expensive than what you have from the grid, means that over the next 5 years, this should be a very interesting opportunity for India to be able to explore. Thank you very much, Ram. You're on mute, Ram. We can't hear you.
Oh, sorry. Yeah. Thank you, Ravin. I mean, I think it's a minor miracle. We got through your presentation. Thank you for staying on. I'm hoping we can get back to you for questions. Maybe the power comes on, or at least if you can, if you're able to keep going on backup power, that'll be great. And maybe you need a small hydrogen electrolyzer in your apartment too. So thank you. So with that, that's a great introduction. I think just keeping on the same topic, what I'd like to do is switch it over to Dr. Krishna to talk about his research and what he's doing to enhance local energy communities. And hopefully, as we go through the panel, we can get those connections happening. So, Dr. Krishna, if you can take the floor, please.
So we are in this group. We span different departments, going from aero to chemical and electrical and humanities department. And we want to look at energy microgrids, as I had mentioned yesterday. And we are interested in the form that these microgrids would take in different geographical areas, which will go from the rural, urban, and the hilly areas as well. And we are looking at how the local energy communities could then be enabled by using this kind of an approach. And here is an interesting graph, which I have used again and again. So this is a look at the sort of microgrids that are available around the world, a small sampling of that, more from the microgrids of the West. So here you have. So the x-axis here represents the sort of energy sources that are used in different areas, different microgrid installations. And the different shades of blue, orange, etc., they basically denote the location, the different installations that are there. And on the y-axis, then you have the energy source capacity that is installed in the various microgrids. And you can see the range of energy sources that have been used in different locations. So here you see that the energy sources range from the normal DG sets, where diesel is the main source. And then you have energy from the sun, energy storage as well, and then a whole range of energy sources. The interesting thing to note is that the number of shades that are there in the energy source, in a specific energy source, indicates then the number of installations that use that. And we can see that here, if you look at energy from the sun, that is the one that is used almost at all locations. But the stark difference that you see is that the energy source capacity here is rather small, and the maximum maximum energy source capacity that is there is basically from diesel. So if you look at the overall approach, as I had mentioned yesterday, as to how the microgrids are really now being used and deployed, is that people are looking at one stable dispatchable source, which is the diesel genset. And then you can then say, I want this much energy, and the diesel genset will give you. But then we want to move towards an energy system where we don't want to use diesel. And if we remove that, then you can see very evidently that a large capacity source is now being eliminated, and you have to now manage with the others. Especially we are looking at managing with these kind of energy sources and not really going into the other varieties which are non-environment friendly. Of course, you have wind and hydel. Hydel, I don't know whether you would call it environment friendly. It is debatable, but wind definitely is. But wind as an energy source, at least for large energy grids, is definitely going to be dependent on whether you have the resource at that specific location or not. So here we see that we have to displace this, and that gives rise to a lot of difficulty in operating the grid. You go to the next slide. So this is essentially, situation from the west. In the east, also we have some information. There are a large number of these deployments and installations in India as well. But here, if you see, the approach is slightly different. We don't have a large variety of sources like what we see in the West, where it has been deployed for at least experimental installations. But what we see here is that solar forms a large part of the installation. So a large number of microgrids that have been deployed in India are basically single source based. There's one reasonably large solar installation which feeds the entire location. That's the major deployment scenario that we have. But there are certain other sources that are deployed as well. You see diesel here also, but the number of installations of diesel in the areas that have been surveyed so far in this exercise is fairly small. But if you look at the installed energy capacity, you see that diesel is still the largest. So again, here in India, if you look at it, diesel plays a very big role in establishing these kind of grids. And when we are going to displace that away, we have significant issues that would be involved in maintaining the grid operation. So with this, So with this, the action envelope that we are intending to take in this area is that we would like to look at the development of the energy source technologies for variety of locations around the world, where depending on the nature of energy source that is available, we would like to look at the development, improvement of energy source technologies, and especially make use of energy sources which are not really very high density. For example, wind, if you take, you have very high amount of wind in extremely specific locations. If you look at all over India, that much wind is not available. But we would like to develop technologies where one can make use of low wind speeds as well. That's an example. And then for the energy grid itself, we would like to develop management methods where one could use these kind of resources, not a very strong resource like diesel. If you are going to use diesel, as far as the grid is concerned, it's small. It is almost like the normal AC grid, right? Because you get any output on demand as far as the capacity is concerned, up to the capacity. But if you don't do that, then we'll have to manage with several resources and still meet the operational needs of the grid. So we don't want to have one source that is going to be very dominant, and see how we can do that. And then the next issue that will arise in this kind of a grid operation is how we are going to manage the operation of the grid. There are installations where the entire operation of the grid is managed by one central operating center. Whether we would need to go for that kind of a mechanism or whether we can develop decentralized approaches. If you look at it, decentralized approaches are probably better in a sense, because each area is in a sense autonomous, right? So this would be good, but then decentralized approaches are much more difficult to implement and operate effectively. We also are looking at approaches where the energy sources are not all located at the same area, at the same exact location, but rather distributed over a larger area, which again brings in ease of installation and operation. But operationally, it's the definite ease of installation, but operationally, it's a little more difficult to handle. But in the work, we are interested to address that. And then we would also like to look at the economics and optimality of all these installations. So similar to what I mentioned yesterday, we are interested first to deploy a grid at IITM, which would then consist of all these different varieties of sources. These are to some extent already under investigation in different departments at IITM, and therefore they are already at different levels of technology development. And we hope to finish these technology developments and then have a deployment as well. And then as we go ahead into the second phase, we also want to include many more technologies, especially wind and for hydro as well, where, as I said, we would like to make use of low energy density resource availability. So at IITM, this sort of shows an overview of where is it we would like to install the grid. So we would have a grid, we expect to have a grid which is going to be stretching from the electrical department at one end of the academic zone and go all the way up to the new academic area on the other end of the academic zone, spanning the entire width of the academic zone. And different sources would be located at different areas. Energy storage is here and other sources are located at different areas. So this is the sort of experimental grid that we would like to install, operate it, and see how the whole thing is able to work. And there is a huge amount of research that's going to be involved in this. So one is with respect to the islanded operation itself, because this grid has to operate along with the main grid as well as operate in isolation. So how does this grid then know whether the main grid exists or is off? Right? So there has to be some method to detect it and then switch over to a different mode of operation where you can independently handle the entire grid. And when these kind of grids operate in isolation, you have to remember that we are not looking at the normal AC generators that are there in the AC generating stations, which automatically generate a nice sinusoidal AC waveform. But we are looking at using high power electronics in order to generate the waveforms, which then means that you are likely to have distortions and that may affect the operation of the loads also. So the question is, how do you maintain the operation of the grid in a normal manner when you are having all sources being operated through inverters? And then you have islanding, how it has to be detected. And once the main grid is going to come back, you need to resynchronize to the grid. So how does one do that as well? And then the economics of operation, optimization, and there is a wide scope of using AI methods in order to learn and operate the grid as well. So I think, that's all I have about the work that we intend to do. Over to you, Ram, again.
Yep. Thank you, Dr. Krishna. That was a good description of what you're trying to do. And let me hand it to Dr. Mani to talk about his research, and then we will go to Karthik.
Okay. Thank you, Dr. Ram. As it is mentioned, I'll be talking on the compact solar desalination and the cold storage systems. It encompasses two projects, namely desalination as well as cold storage. The need of desalination system doesn't warrant any emphasis, as it is mentioned in the second point. Out of 2.5% of the water which is available of good quality in the world, only 20% is available for the human consumption. Hence, we require to concentrate on the desalination system. Depending upon the source of water quality, whether it is a brackish water or the sea water, depending upon the quality of water that you wanted to get, in the sense how many parts per million salt content as to present in the water, depending upon the techno-economic aspect of the system, appropriate desalination systems required to be used. Out of that, we choose an multi-effect desalination system. Using solar energy, we can produce, using solar flat plate collector, we can heat up the water to 60 or 70 degrees Celsius. By flashing that water, we can produce the water vapor. By condensing that water vapor through the tubular heat exchanger, by spraying the seawater over that, we can produce the steam. Simultaneously, we can condense that water vapor, and that will be forming as a condensate. So this is the first effect. This will be cascaded, second effect, third effect, so on. Finally, the water vapor which is produced in the last effect is condensed, and fresh water is taken out. The remaining brine is taken out, and the seawater is taken and it is circulated through the system. The entire system will be maintained in the vacuum condition. So that is done by means of using two-phase ejector. So here, what we are intending to do as a part of the research work here is, we wanted to enhance the efficiency of the evaporator, which is normally made with the plain tube. Instead of plain tube, we wanted to use a thermally spray coated tube or metal foamed wrapped tubes. So for this kind of heat transfer enhanced surfaces, we would like to study the heat and mass transfer characteristics. For that, we'll be using non-contact type of transducers to measure the film thickness around the periphery of the tube as well as in the longitudinal direction, and compare these measuring techniques with the technique which is available in the literature, and also to understand the operational effect of the desalination system. So this is a simple schematic system for carrying out the experimentation. So this is the tube over which that we will be carrying out the thickness of the film which is flowing over the tube in the form of falling film. This is the schematic diagram. So this kind of schematic diagram has been attempted in the laboratory, and we are able to get the falling film thickness in the form of ultrasonic amplitudes with the different colors, without flow, with the flow, etc. From this, we can infer what will be the thickness of the film. And this has been compared with the data which is available in the literature with that of the Nusselt, Wu, and our studies. See how the things are comparing well. Then, and also we try to compare the falling film measurement with the contact type as well as our air coupled non-contact type of ultrasonic sensors, and see the difference. Almost there is no difference here. And while carrying out this research, while we noticed that the foam which is used for wrapping around the tubes, we found the hollowness. So what will be the effect of hollowness on the effective thermal conductivity of the system that we would like to carry out? For that, we use this X-ray tube machine for placing the sample here to carry out the microtomography studies for the metallic foam that will be used here. So these are the different structures that will be arrived at based on the microtomography. And if you try to fill up that pores with the vacuum or air or water, if it is a solid copper, how the thermal conductivity of this metal foam varies, that has been deduced. And all these details are presented in the International Journal of Heat and Mass Transfer, which has been published during the year 2020. Then, and we carried out similar studies by means of using laser interferometry. We repeated the same thing. to get the enhanced effect so that we can carry out the transient phenomena measurements also. For that, the typical schematic diagram is shown here. We use the testing tube that required to be used for carrying out the measurement. These are the dummy tubes that will be used here to develop the flow. And we can carry on all the permutation combination to meet out the desalination system requirement. So these are typical system which has been established in the laboratory to carry out the experimentation on the optical table using MZI interferometric techniques. So using that, we are able to capture the real image, which is converted into binary image by means of using the code. From that, we process the system and we got the processed binary image. From that, we try to infer what is the film thickness and the interface temperatures. For that, this flowchart is used for carrying out the studies. And by that, we try to infer what will be the thickness of the film around the periphery of the tube, which has been compared with the information which is available in the literature. That's how it changes. And also, we try to compare the heat transfer coefficient that we evaluated using the study with that of the nacelle. So that's how the comparison comes into picture. Later, we carried out the film thickness measurement by varying the flow rate on the circumference of the tube, and it varies like this. Then also we try to measure the interface temperatures around the tube like this. Then these are all the visible outcomes which has been produced based on the studies which is carried out by student after carrying out the work. These are some of the work which has been published related to our group in the journals which are all available in the literature. These are the references. Then next I'll move on to the compact solar refrigeration system. It doesn't warrant any emphasis. You can see that about 92,000 crores of food is getting wasted due to lack of cold storage and also the refrigerated transport. So because of that, we require to look at affordable cold storage system. The conventional cold storage system or the refrigeration system operates with compressor, condenser, expansion device, and evaporator. So here, to use high-grade energy in the form of electrical energy as the input, we require to get this energy which has underwent conversion elsewhere. Instead of that, we wanted to try with a thermally operated system which is driven by means of using heat, which is called heat-driven absorption refrigeration system or heat-driven vapor jet refrigeration system. So this we call it as a thermal compressor, which will be consisting of the heat exchanger called generator, absorber, expansion device, and the solution pump. And the irreversibilities comes into picture in this absorber and generator. Hence, we wanted to concentrate to enhancing the heat and mass transfer effectiveness of the absorber as well as generator. So typically the schematic diagram of the absorber is shown here, where the refrigerant vapor is get absorbed in the weak two-component solution which is coming into the pipe. So here, while doing so, we'll be looking at the global warming potential and also the ozone depleting potential, and we'll be selecting the appropriate refrigerant which will be environmentally friendly to carry on these studies. So here we used 134A as a refrigerant and 134A DMF. DMF stands for dimethyl formamide for the solution. So here, to understand the heat and mass transfer characteristics, we wanted to introduce the swell entry for the gas, the refrigerant gas which is entering into the system. By that, we increase the residential time of the refrigerant in the solution. Thereby, effectively, the absorption of the refrigerant vapor will be taking place. For that, we carry out the bubble visualization studies in the tubular absorber as well as the compact absorber, and we carry out the detailed experimentation in the laboratory. Similarly, we carry out detailed studies with the generator too. So here also we'll be using the swell entry for enhancing the residential time to enhance the heat and mass transfer. Thereby, we get a better heat and mass transfer effectiveness for the evaporator. Consequently, we can get a better coefficient of performance of the absorption refrigeration system. The sweller has been designed by using this kind of profile, which is shown in figure number 22A, and the typical generator which has been generated for the swell is shown in figure number 22B, and 3D printed swell generated in the laboratory is shown in figure number 22C. So this has been used for visualizing the fluid flow which is taking place in the glass bubble absorber. This has been fabricated and the studies has been carried out. The photographic system is shown in figure number 23B, and schematic arrangement is shown in figure number 23A. And this system has been built in the laboratory and the experimentation has been carried out. There are three possible ways that we can carry out the system. The solution can be retained in still condition, or it can be moved in the co-current direction as well as in the counter current direction. All three ways we are able to carry out the experimentation, and this work has been published in the Purdue conference during last July in 2021 in the Purdue conference. And using that, these were some of the work which already been carried out by our research group in this direction. Then on the vapor jet refrigeration system, we also carry out the work, and the schematic diagram of the vapor jet refrigeration system is shown here, which consists of the component like generator, ejector, evaporator, condenser, expansion device, and the refrigerant pump. So the typical ejector is shown by the line diagram here, which will be containing the primary convergent divergent nozzle, which converts the pressure of the working fluid into the kinetic energy at supersonic condition. Due to exchange of momentum between the stream which is coming through the nozzle is called the primary stream, which exchanges momentum with the fluid which is present around us. Due to momentum exchange, it is entrained. So this entrained fluid is called the secondary stream. Both the primary stream and the secondary stream will be get mixed up in the mixing chamber. To carry on this mixing phenomena effectively, we try to introduce the swell here. Thereby, the effective momentum exchange will be taking place. Consequently, that will be diffused through the diffuser. Thereby, the effectiveness of the ejector is enhanced. So that has been
we have 1 minute.
That has been attempted in the laboratory. So we do the Schlieren visualization techniques and also particle image velocity metry for carrying out these studies. And some of the studies are carried out in the laboratory by means of using a solid type of vanes and the cavity type of vanes, and that is used in the ejector. By using such a system, we are able to get the characteristics of the ejector like this. ER stands for the entrainment ratio, which is defined as the ratio of secondary stream flow rate to the primary stream flow rate. And DR stands for the driving pressure ratio, which is the pressure ratio of generator pressure to the expansion pressure, evaporator pressure. So you can see the cavity type of swell generator enhances the entrainment ratio. And these characteristics are detailed way it is presented. I will take another 1 or 2 minutes. So that Schlieren experimental study has been carried out in the laboratory, and the Schlieren work has been done, which is compared with the CFD work, which is carried out in the experiment using laboratory visualization techniques. And we try to capture the transient phenomena also, which is presented in figure number 39. So these are the outcomes of the group which is working on this system. So that is about, so by this, what we intended to do is we wanted to enhance the entrainment ratio of the vapor jet refrigeration system. Thereby, we wanted to improve upon the coefficient of performance of the solar operated vapor jet refrigeration system. Thank you.
Thank you, Dr. Mani. And I think you started the discussion with a discussion of the food wastage. And I would like to invite Karthik to talk about how Waycool is started with that vision and what they're doing today. So, Karthik?
Thank you, Ram.
Yeah.
I'd like to, firstly, I think I got a lot of the answers that I was looking for already from this seminar. So it's been very useful for me. Thank you, all of you. But I'd like to start with, I'd like to take my conversation through in the following steps. I represent the user, and we are a large user of thermal management and humidity management in the business that we do. I'll start with an introduction of the company, which is a short video, and then I'll talk a bit about the problems that we have solved so far and the problems that we have to still solve. I'll request that a short video be played. Thank you. We are way cool. We were formed 6 years ago with the intent of revisiting how food moves from soil to sale. I think Dr. Mani touched upon the point of the kind of food waste that one sees. I think in the industry, we split the language as food loss and food waste. Food loss is what happens from the farm gate to the supermarket shelf. Food waste is what happens at and after the supermarket shelf. If we compare what happens in India versus what happens in the West, both these geographies estimate a combined loss plus waste of about 35 to 40%. What that means in our context is that we lose as much food as what Brazil consumes in a year. That's the extent of food loss that is estimated. Nobody knows the real number. Honestly, these are guesstimates. The difference, however, is in the West, most of it is food waste. Very little gets lost from the farm gate to the consumption, to the supermarket shelf. Supermarket shelves waste 25% of fresh produce, for example. And at home, in the refrigerator, there's considerable amount of wastage. Here, we don't waste much food. We sell pretty much, all our shops are small shops, and they sell by variably pricing the product. By the end of the day, the shops are empty. We don't waste much food at home either because we are small, frequent purchasers of food. The loss, however, is about 35%. And the reason for this loss is the length of the supply chain. And the reason for the length of the supply chain is the fragmentation of production and fragmentation of consumption. We have a large number of smallhold farmers. The small farm produces a limited quantity of output, and that needs to be consolidated. So you have multiple layers of consolidators. On the other end, you have to break down the full truck that arrives into, say, Coimbatore market over here and deliver 25 kgs at the nearby corner shop that we buy our food from. That results in disaggregators. Therefore, we have repetitive transport and handling, multiple thermal conditions in which sensitive products such as fresh produce moves, and consequently significant loss. What we run is a direct supply chain. We work with a large network of farmers, as you saw. We engage from the cultivation process itself to make sure that their planning is in line with demand, and we move the produce and products directly where they were required through a processing center, but otherwise we collect the produce in a collection center, organize the produce, ship it directly to distribution centers and consumption areas, and from there directly to the retail outlets. So it's a 3 or 4 step process. We are committed to operating this as a net zero supply chain at the earliest possible date. We heard a date of 2047. My company says they want to get there by 2030. It's a big challenge. We said scope 1 and scope 2, at least we should get to net zero by 2030. Scope 3 is a more challenging solution to get there. And the way we are looking at this is, if you look at the sources of carbon emissions, we have transportation. We have, of course, cultivation itself. the process of pumping water out and cultivation practices, drip systems, etc. We have the transportation process, the material handling and storage, particularly temperature controlled and humidity controlled storage activities. And then you have basic lighting and illumination and other loads that make up the emission and energy loads. The approach that we've taken is threefold. First, reduce the need for the activity itself. The second is reduce the electric load or the energy load or the emission load of that activity. And the third is to switch to alternative energy to support the residual load. How do we reduce the need for the activity itself? For example, we're working on projects to reduce food miles. We are discovering agroclimatic conditions closer to consumption points and moving certain crops and growing them closer to the consumption point so that the kilometerage itself reduces. One good case study is what we have done in the case of what's called as exotic vegetables, such as broccoli and lettuces and so on. Bangalore is one of the largest markets to consume these products. Most of these are grown in the Nilgiris. If I move the material from Nilgiris to Bangalore, I'm moving it across temperature zones that are widely varying. I have to use refrigerated trucks. The product arrives a day later, it loses moisture, and therefore if I load 1 ton, I get about 800 kg in this when it reaches. And the residual shelf life is very poor. The challenge that we face, particularly in fresh produce, is that these products cannot take thermal shock. I can bring it in a reefer. I can even temperature control my warehouse. But the moment it reaches the shop, it's out there in the open. So what happens when it goes from 2 degrees to 20 degrees? The product actually perishes very, very fast. So these are some of the challenges that we face. In this particular example, what we did was we discovered a zone that's just 30 kilometers from Bangalore, which is suitable for cultivation of the same crop. So today, when a customer orders, we simply pull it out of the ground and go and deliver. We don't even need a refrigerated truck. So this eliminates the need for a few activities. The second thing that we have done is to see how load can be reduced. We've made some progress in this area, but we need to make a lot more progress. The easiest ones to attack was obviously lighting load, fan loads, etc. We went to BLDC fans, we went to LED lighting, and then we put in fact, I think Professor Junjunwala was referring to a rooftop cafeteria. We already have a solar cafeteria. We built a cafeteria with a solar roof. Our factories are now off-grid during the day. Many of our warehouses are off-grid during the day for at least these loads. We were also able to support transit cold storages, which are 1 or 1.5 ton load storages. We have about 4 or 5 of these. If you're having a throughput of say 60 to 70 tons per day, which is a typical warehouse load. However, that is not enough. Our biggest challenge is what I touched upon earlier, the thermal and humidity management of these products. We have a number of initiatives around cold storages. The problem that we face is that all of these initiatives are focused on taking the product down to 2 to 8 degrees Celsius, which is necessary for extending the shelf life of the product to say 21 days or 30 days. What happens when I take it in 2 to 8 degrees Celsius is then I have to move the product. For example, I remove the field heat of a say cabbage, which we harvest at 37 degrees Celsius near Krishnagiri. I have to take the field heat out, bring it to a certain point, and then further cool it to about 2 degrees Celsius. And the reefer has to carry it at the same 2 to 8 degrees Celsius, which means the load on the reefer is very, very high. The load on the engine is very high. A lot of those loads get added up. And then it comes to my warehouse. I have to put this in transit cold storages. And we are dealing with small, low value, unwieldy products. If I'm going to chill the entire warehouse at that temperature, then it becomes extremely expensive for me to do so, and the product will not support that cost. And after I do all of this, I have no control over what the shop has done. Now, we found some via media solution over here. What we've tried to do is the following. We realized, and we spoke to folks in the FAO, and they came back and said, hey, India is not a supply chain where you need long storage. You don't need to extend your shelf life to 30 days. Your clients buy our fresh produce every 2 or 3 days. Even if you can extend it to a week from farm to consumption, that's good enough. And every degree of temperature drop increases your shelf life, reduces the metabolism rate, etc., and increases your shelf life by so much. Even if you try to operate at between 18 and 20, which is air conditioning load, you should be okay, provided you manage the humidity well. This was the broad guidance that we got. So what we're now trying to do is to establish a supply chain that operates uniformly at 18 to 23 degrees Celsius. Secondly, the challenge in operating this is it's easy for me to, for example, remove the field heat. I don't even need a field heat removal system at the farm. My truck itself can remove the field heat. I can actually cool the material in the truck itself, and I can hold it at 18 to 20 degrees Celsius by the time it reaches, for example, Chennai. The challenge happens at my warehouse. I am able to cool small closed spaces very effectively. But my warehouse is 5.6 meters tall because, as you saw, we automate our warehouses. There are a lot of machines, conveyors and robots that are moving around. I need a high roof. And I don't build my warehouses. We lease warehouses where available because we can't afford to build our warehouses. How do we cool a warehouse at 18 to 20 degrees Celsius? Second, how do I maintain multiple zones of humidity in the same warehouse? For example, I cannot have relative humidity of greater than 60% for onion, which is the largest consumed vegetable. I have to have 85 to 95% RH for fresh produce. My humans cannot work at 85 to 95% RH. They have to work at 65 to 70% RH. So how do I create multiple humidity zones is one of the challenges that we're doing. Secondly, my rooftop was enough to power my transit cold storages and my illumination and fan loads. My rooftop is not enough to power cooling of my entire warehouse if I use traditional air conditioning systems or even partial refrigeration systems. What is the way by which I can consume less energy while doing this? And the third is I can't afford to partition my warehouse into multiple closed zones also. If I partition into multiple closed zones, movement of the goods is hindered. And we face a very, very strange challenge in our industry. For example, all the fresh produce, 60 tons of it moves through our warehouse in just 3 hours. Because the harvest happens in the morning, by the time it reaches Chennai city, it's 1 in the night. It has to leave by 4 in the morning from our warehouse. So if I have too many hindrances, it becomes very, very challenging for me to move material smoothly. I will always have residual material left over, which will be sold the next day. So typically we operate in a 60-40 model. 60% of the material is flow through, 40% is held back for the next day or so. So this is the kind of complex situation that we face in our warehouse. What we're exploring, for example, one of the projects that the team is working on is, can we use a solar-powered heat pump? We have hot process water requirement for cleaning and other purposes. Can I take heat from the warehouse and somehow pump it into the process water and therefore create efficiencies on both sides? This is one of the projects that the team is working on. They're trying to see whether there can be a solution that humidifies on one side and dehumidifies on the other. The challenge I face there is I cannot have cross-contamination. I cannot have the same air that flows over my onions, flow over my lettuce, because there will be cross-contamination of gases and tastes. So these are the kind of challenges that we are facing at present. And it is actually to address some of those challenges that we are seeking active partnerships. We're working with a number of institutions, and I see a lot of learning that I got here today. I'm hoping to pick up a lot of potential projects that we can work with the IIT team on. So Ram, I'll pause here. I'm happy to.
Thank you so much. Thanks, Karthik. I know we have another maybe 20 minutes, so I just wanted to move on to the panel discussion. I think we also have Pashu, who's joined us on the panel. Welcome. So, having heard the two sides, right, from the customer side and from the research side, I wanted to maybe start from the end. So, Karthik raised a question of solar-driven heat pump processes to move heat back and forth. And I wanted to put it out to our panel. I think, Dr. Satya, you're also working on something around heat pumps. I wanted to see what your thoughts are in terms of IITM being able to work with a customer to be able to address the challenges around the energy use and energy affordability.
Thank you, Ram. Thanks for putting that out. So I think IITM has evolved quite a bit. There is a wide range of activity from what you saw with Dr. Mani working on early stage technology demonstration to also working with industries on field deployment, and in fact, even doing beyond field deployment with a couple of pilots. So I do work with a couple of companies on heat pumps where it's an energy efficiency device for industrial heating and taking the objective is to get rid of your boiler or fire your boiler. So we've done that. I think there is a lot of scope and opportunity. And in fact, IITM has also spanned out a couple of startups. You might be aware of TAN90 being one of them, which precisely started tackling some of these farm gate problems, last mile, first mile. So there is quite a bit of scope. And I think as Professor Ashok put it out in the last panel, clear articulation of problem statements would really help. And I think there are opportunities to work together and scale things quite fast.
Thank you. Dr. Mani, do you have any thoughts on the needs that Karthik expressed?
Here, to the extent possible, the heat load to the warehouse can be reduced. That is one. And the heat which is available there can be used for humidification purpose to get a humidified air for preservation of the vegetables. And of course, the air which can be drawn over desiccants can dehumidify, and that can be used. Of course, the effect of desiccant wheel that will be used for dehumidification has to be studied here on the vegetables. For experimentation, it's okay, but for the food product, that has to be looked at, and that has to be experimented.
Okay, thank you.
Of course, as he was mentioning, the heat-operated system can be thought of. Even the photovoltaic power which is produced nowadays, the Danfoss makes a DC compressor that can be coupled to produce the cooling that can be thought of. Even the vehicle which are all transporting the vegetables, fruits, that can be equipped with that kind of system too. Rooftop mounted photovoltaic panels can produce the power that can be drive the cold store system like that.
Great.
Of course,
okay, thanks, Dr. Mani. Yeah.
the conversion efficiency of the photovoltaic panel will be keep changing because the orientation of the panel will be keep changing. Because of that, it will be subjected to change in conversion efficiency. All these things has to be looked into.
Great. Thank you. So I think that's again a foundation for people to start working together, right? So the goal here is to kind of highlight the fact that the research at IITM spans a whole range of different issues, whether it's looking at renewables integration into the grid, looking at demand response and thermal storage, or looking at how do you help customers reduce their energy costs, energy bills, and solve specific problems. So on that same note, I wanted to see if Ravin talked about the hydrogen electrolyzers that they're working on, and Dr. Krishna talked a little bit about the microgrid research. And I also wanted to welcome Pashu to the panel, if he's there, and just see what is the role of hydrogen in these local energy communities. And I would like to open it up to to Dr. Krishna and others too, to maybe have a little bit of a discussion of the role of hydrogen in these local energy communities in India, how the models that Ravin talked about in Sweden or in Europe are translatable to India, and how that fits with the research, or how you would tailor your research to serve the to work with Ravin.
Yeah. So the role of hydrogen as an energy storage, in order to convert excess energy that's available into some form, I think hydrogen would be a very good option for the local energy communities, provided we make it economical enough. At the moment, I think the economics is the one that's really hindering this. And if we can, as I was just discussing with some people over the dinner, I think if we can achieve a level of decentralization for hydrogen generation, which can possibly fit into the local energy communities as well. But the essence would be to look at what scale this would become attractive for implementation. If that can be achieved, I think this will be very useful at the community level. Yeah, I also had another aspect to ask to you. You mentioned that if you maintain a temperature of about 18 to 20 degrees in your house, in the storehouse, it's quite adequate. But have you done any investigation on when the atmosphere is 18 to 20 degrees? is it 18 to 20 degrees at the vegetable also? Because I would assume that there may be considerable difference between the ambient air and the level of temperature at the actual vegetable or whatever is being used. And therefore, if there is a difference, then by sort of reducing the space of air conditioning, but instead of air conditioning the entire room to 18 degrees, maybe you could look at smaller spaces which are maintained at a temperature at which the vegetable really is. Maybe not 18 degrees, maybe higher as well. No, absolutely, Professor. I think this is one of the challenges. When, for example, we can't just load harvested produce into a truck, which is already pre-chilled. It is punishing for the commodity. We will have to drop the temperature down gradually so that by the time the vehicle reaches, for example, from Hosur to Chennai, it is largely at 18 to 20 degrees Celsius. And if I do that, and if my warehouse is at the same temperature, then the product is not punished as much. However, if I'm actually, for example, getting it from Coimbatore market and bringing it, it is going to be very, very punishing. And you're right, maybe we will need a curtained off space where we operate at a different temperature and maybe draw the temperature down almost as a pre-cooling or a field heat removal process. I think it is necessary for us.
So just to add, in this discussions we had earlier in the day during our IT and earlier session, there's a lot of talk about hydrogen and how maybe we are not looking at hydrogen the right way. But what Ravin shared today was something exciting. There have been quite a few demonstrations. So maybe I'll open the session up for a few questions from the audience as to if they want to ask about the hydrogen experience of Ravin and see if there's something that we want to learn from.
Yeah. Dr. Satya, I think there are a few questions on the Q&A around hydrogen. So I know that I think that maybe I will just bring up those questions. So one is water intensity of hydrogen is about 15 to 22 liters. And given the scarcity of water, does this mean we have to use desalination for hydrogen production? So Ravin, I mean, your thoughts, I know you put it on the chat, but any additional thoughts on that topic?
Ram,
because that's a big topic, yeah.
It is, and I'll answer both the questions. One is whether hydrogen is an efficient use of energy, and two, the cost of desalination, because they're both headed in the same direction, and that is, is this the best way to, and is this the most cost optimal way to do energy? And the truth is, we're looking at this from the perspective of the last 100 years, but we had only one way to make energy. And we're moving to a future where there's going to be a myriad ways to make energy, and we will be agnostic to the technical competencies of making it and the efficiencies of making it, and it'll come down to the use case. So if I come to the Maldives, if you look at the fact that they import diesel from Saudi Arabia and then distribute it to little islands, having to transship it 3 times, the cost of energy that gets to the ultimate island is incredibly expensive. In a context like that, when you look at desalination, albeit incredibly expensive in Chennai, might actually prove to be cost effective in a location like the Maldives. So it depends on the use case. Hydrogen will be used in areas where you have a lot of sun and a lot of wind and a lot of water. 90% of the use case of hydrogen will be in locations like that. So Leh, for example, will be an ideal candidate to move to hydrogen, because why would you truck diesel all the way up there or try to wheel electricity all the way up there in such an expensive and tenuous manner, because it can be impacted so easily through line breaks. Maldives is another example. Antarctica would be another example. So it depends on your use case. The other question was, hydrogen has come under a lot of flack because it's not the most efficient use of energy. Yes, that's true. However, when you fly, for example, from Amsterdam to London today over the North Sea, there are thousands of windmills that are not working because they're generating too much wind for the grid to be able to take, or for the batteries to be able to take. In a context like that, that energy is wasted. You have energy that you're not able to make with all the assets that you have already deployed. In this context, then having a marginal increase in your capital to generate hydrogen for energy that you could not generate anyway, the context is quite different. If you're going to compare hydrogen to, hey, I've got coal being generated, or I've got LNG generating electricity, or I've got solar generating electricity, it's a very different argument to, I've got these assets that have been invested that I cannot use because when I have too much renewables, I don't have enough storage, or the grid cannot take that amount of energy. And then when I have demand, these assets have been switched off. So I would come back down to the future of energy is a use case based investment. And you might, in fact, make investments in what you would conventionally consider inefficient just because your use case makes it efficient in that context.
I just have a follow-up question to that, Ravin. So do you then really, to make sense of the big push for green hydrogen is really to soak up the solar that might come on the grid and not really about hydrogen?
You're absolutely right. The start of the energy revolution with hydrogen will be exactly that. Soak up the renewables, whether it's solar or wind, that you're not able to use today because the cost of battery is high or the grid is not able to absorb it, and therefore store it as hydrogen and then transport it very efficiently to another location of use, or store it in that point of use to be converted back by a fuel cell back to hydrogen. Over time, however, that will change. For example, we are today involved in a project funding a university in Sweden to reduce the cost of generating electricity through electrolyzers and the cost of converting it back to electricity through fuel cells by using electrodes that are not rare earth materials. So today you have to use titanium and platinum in electrolyzers and fuel cells. Over time, as technology develops, if we are able, which I'm very confident we will be able to over the decade, use materials that are not rare earth materials and reduce the cost of capital, you will find that the whole use case calculation changes. And therefore, villages that are fringe of grid in large parts of India can convert to being solar hydrogen rather than having a 10 years grid that is supplying them with one electricity line over 100 kilometers.
Before we close, just one. You have taken your bet on hydrogen. What do you think will happen to batteries?
Is that a question to me?
Yeah.
I would say it's horses for courses, because today, you're comparing it to lithium ion, incredibly expensive, and it uses lots of rare earths as well, because you've got cobalt, manganese, all sorts of other materials that go into it. However, the cost of lithium batteries drop, as you know, 22% almost every 18 months. So that will change your calculations. And then in the future, if you're talking about static energy applications, you might be able to use sodium ion. You might be able to use a superconductor. So as these technologies evolve, you will have a different use case argument for every investment that you make. So it'll not just be what we do today, which is coal-fired power for every application. It'll be based on where you are, the geography you are, the energy mix that you have, and what is available to you, hydrogen, sodium ion, superconductors, graphite, lithium, that will help you make the decision.
Nice, nicely put. That's kind of what we are trying to understand through our microgrid work. So we have one more question here from the audience. Vasu?
Yeah, I would like to hear, because I heard a lot about Sweden, all these off-grid and all that. What is the scale of economic change that needs to happen before it's applicable in India, from an economics perspective? Because it can be very wide, or is it like 10 years? I mean, then once we understand the economics, we can translate into time. Is it 5 years away, 10 years away, 25 years away for these kind of solutions to be applicable?
Okay, very good question. And thank you so much for asking that. So, in India, we are constrained by the last 70 years of our existence, where we had to be frugal and didn't have a lot of resources. And so we had to be incredibly frugal in where we deploy them. So L1 is our mentality, and lowest cost is going to be the way we decide how we're going to implement our energy future. The hydrogen strategies of both Europe and Australia are to generate hydrogen at €2 a kg by the end of this decade. In order for that to happen, a number of things have to happen. First is scale in renewable generation, scale in electrolyzer manufacturing, and scale in fuel cell manufacturing, and then to be able to not use rare earths in electrolyzer and fuel cell manufacturing to be able to generate at a little low capital cost. I am fully confident that we will be able to achieve that cost of hydrogen by the end of this decade, particularly because Reliance has committed to making the largest gigawatt factory for electrolyzers in the world in the next 4 years. So we will see the whole wave that Reliance created, not only with petrochemicals, but also with geo happen in hydrogen generation over time. Once we get to $2 or under, I think the use case changes very rapidly for disconnected communities and fringe of grid communities in India. So to answer your question, we need to get to less than $2 for this to be interesting to India. When will that happen? My own estimate would be 2026, 27. Where it will start to be interesting for static energy applications in India. I'm not quite sure what that means for mobility applications in India yet.
Hi,
So we are right at 9:30.
Ram, I think Pashupathy didn't
yeah,
talk at all. I guess he was also in the panel. Pashupathy, Ram?
Yes, I'm sorry, I don't know. I don't see him on the panel.
Oh, okay. Okay. That's fine. Then. Yeah, that's
yeah.
fine.
Yeah, I think, yeah. Go ahead, Ram.
Okay, so I was going to close out. I think there's maybe one audience question. If we can take maybe 1 minute to ask to do the audience question, and then we'll do a quick closing round. I know we are right at 9:30, so we'll try to do a closing round after that. Is there one last audience question? Are we good?
Yeah, there's one more here.
Okay.
Hi, Krishna, question to you. Listen to your stuff yesterday as well as today on microgrids. Your main point was, even though microgrids supposed to be BER with a lot of renewables, mostly it is actually offsetting diesel, right? But assuming we are able to get microgrids even to a larger level in terms of other renewables, have you guys done any work on what is the extent of decarbonization that's possible? I know it's tough, but I guess that's part of the reason we are going microgrids as well.
So, yes.
Or some kind of a carbon footprint evaluation for the microgrids?
We have not yet looked at it from that aspect. That's one of the agenda items in the research that we intend to do now. Right? How does the actual emission footprint look like, and how we can bring it down? Now, the way establishment of microgrids themselves go, the goal of emission reduction is not necessarily the only goal. Having energy security in the face of disasters that may happen, where if you have a grid which is going to supply energy to you, in the case of disasters, the grid gets cut off, then you have an entire area that's devoid of supply. Now, if that area had been endowed with local energy sources which have been connected, usually now if you look at the way the energy resources, for example, if you're going to have rooftop solar, the way it is installed, and majority of the installations are operating in a way that they are interconnected to the grid, and they will work as long as the grid is available. Once the grid gets cut off, even though you may have an installation sitting, it's of no use. Now, if you had this sort of a technology implemented where this installation can still supply energy in spite of loss of grid, you now have an additional use case that is built upon energy security for the region. So reducing the emission footprint is not necessarily the only goal.
So I'll just add one small thing to that. So part of the work we have done, right, shows that the losses or the emissions reductions in microgrid can be substantial if you can electrify your building loads, use renewables, and then manage your losses on the batteries. So it's a series of things that you have to manage to reduce your emission footprints. But you can get substantial reductions as long as your grid generation is clean. So places where it's dominated by natural gas and there's no coal, there's substantial emission reductions from microgrids. So sorry to chime in. I wanted to do one last quick round. So the topic here was around going from technology to pilots to practice. That was the theme of what we were trying to do. So what I want to do is go back to our industry panelists and ask them for pilot ideas that might be implementable, that would be helpful for them. And hopefully that provides more information and ideas flowing from the IITM faculty for us to be able to develop more pilots, get things out of the lab into the field, do the pilots so that we can scale these technologies. So Karthik, do you want to start on this one, on ideas for pilots?
Sure, definitely, Ram. I think we're already talking about a couple of pilots. One is in one of our large warehouses in Chennai itself. We're trying to see whether we can create this multi-zone thermal and humidity management system, which is completely runnable off the rooftop solar that we have. So that's something that we would like to take on immediately and explore. The second is, which I didn't touch upon earlier, is storage, because I run my warehouses in the night. My solar power is on during the day. If I can come in the very, very low cost storage solution, it cannot be batteries. It has to be an alternative solution so that it works out for me economically. That would be another area that I'll be very keen to explore.
Thank you. Ravin, your thoughts on pilots?
It's a very good question, Ram. And I would say a pilot would have to be an area where energy is very expensive to wheel or transport in parts of rural India. So, I'm thinking parts of the Northeast where, wheeling the grid is incredibly expensive. And therefore, today, diesel is transported by trucks. And then you have your average pilferage and you have the emissions. So a hydrogen pilot in such a location or in parts of remote central India where you have the same problems would be very interesting.
Thank you. Thanks, Ravin. With that, I'll hand it off to Dr. Satya to have any closing comments since he's in the room.
I think we've had fairly good and wonderful discussions. This session is virtual, but before this session, we had a offline discussion where heated debates about hydrogen was the theme. We've gotten great ideas and examples from Ravin and also good use cases on alternative storages. All of these are local. Each one satisfies a specific demand. And the previous session also talked about the same thing. Decarbonization is not going to happen at one source or one sink level. It's going to be a combination of many, many things. So we've heard quite a bit from our panelists, and I think we all take away actions that we could possibly do. So with that, I would like to thank all the panelists who are here. Thank you, Ram, for getting up or coming online quite early in there, I believe. So thank you once again, and especially thank you, Ravin, for joining us and staying all through in candlelight. Really happy to see you. Thank you very much. And I request our CEO of the Energy Consortium, Dr. Nikhil Tambe, to come and close the sessions.
Thank you. And thanks to all the panelists and the ones on the ground and remote. So thank you very much.
All right. It's been a slightly longish evening, but I really appreciate everyone's attention. I've been making a lot of notes. I'm sure you had your time to catch up on a lot of things that's been happening over the last two sessions. And we have two more tomorrow. But I just wanted to quickly talk about a few things which are my key takeaways. I'm sure some of these are yours as well. See, we talked about some of the technologies which are really futuristic, some of the things which are right now on the ground. I think the key is to stay aspirational yet be pragmatic. Think of which solutions are really going to work. Professor Junjunwala did stress on the economic analysis. So I think that's a very key takeaway for any technologies to have. And I'm going to actually introduce a term which we can talk more tomorrow, is a CRL. We talk a lot about TRL, and we should as technologists. But there's also something on the commercial readiness levels that we need to be aware of, and that also has the same levels from 1 to 9. So, tracking at each level does not mean we need to know the cost of the product when even the technology is not yet fully invented, but it is important nonetheless. We covered a lot of aspects on storage. Innovative storage did come up towards the end. So I think that's a interesting new avenue. We didn't talk a lot about that in the previous session. So that's something to keep eyes on beyond batteries, what's out there. We clearly heard a lot of challenges from the first panel in terms of scale, in terms of cost, in terms of getting the lithium material, right? So I think there's a lot to think about. We talked about energy security. We talked about supply chain trap. We don't want to get in a supply chain trap with the battery materials that we have. So absolutely important. And ultimately, we also talked about how to drive responsible use of energy, right? How to make sure that what we are consuming today is done in a more responsible way. And I think we had some fantastic examples just now from both the industry participants on how we can do case studies and pilot demonstrations. And I think I loved what Professor Krishna Vasudevan was showing there with the map of IIT. I mean, this campus is a hub where you can think of this as a microcosm of some of the use cases that are out there and use it to study some of these examples. So I think it's a perfect blend for us to take away that, we have industry here to tell about the specific problem statements. And as technologists, we should certainly push them a little more on, what is it that matters the most? And cost often is what everybody will talk about, but it's not the only important thing. So I think that's something that I will suggest everyone to think about. So thanks very much. I'm sure you had a lot more takeaways than I did over here. See you all tomorrow, including the virtual participants. Thanks for staying late, everyone. See you tomorrow evening for the first session at 4 in person and at 6 o'clock for our hybrid sessions. Thanks and have a nice evening.